Okay, thank you. So now we've seen that permafrost is very important. It has major impacts on communities and infrastructure, and it's very important that we as scientists go out into the field, monitor the permafrost, understand the permafrost, so we can better deal with these changes. However, as we've heard, permafrost is not just important for the Arctic. It has an impact on the climate of the whole globe. So when we think about the Earth's climate and climate change, that leads us to climate models, and also the IPCC, the Intergovernmental Panel on Climate Change. The IPCC produces a report showing the latest results from climate models, and this is used to inform policy decisions. For example, when it comes to reducing carbon emissions or preparing strategies to adapt to possible future changes. I say possible because, of course, the future is never certain. It depends on our decisions. So, for example, a world where we reduce our carbon emissions to nothing in the next 20 years is going to look very, very different from a world where we continue with this business as usual, emitting carbon and burning fossil fuels at a very high rate. And this is why we have scenarios. So these represent a range of possibilities between this high mitigation strategy, where we reduce our carbon emissions a lot, right up to this business as usual strategy where we continue burning fossil fuels and emitting a lot of carbon. These scenarios are agreed on an international level so that when we run a climate model, our results are somehow comparable between different institutions. So now we see some results from the latest IPCC report. These plots show the warming that's predicted by the models on average by the end of this century. On the left, we have a strong mitigation strategy, which is known as RCP 2.6. And in this scenario, carbon emissions are reduced almost to nothing, and even some carbon is taken back out of the atmosphere. And you can see here we have quite a low warming. The colors suggest maybe 1 to 2 degrees of warming over most of the Earth. On the other side, we have the business as usual scenario, where we continue with high carbon emissions, and here we have a lot more warming. For example, over most of the land surface, you can see it's about 5 to 6 degrees of warming by the end of the century, which could be catastrophic for humans and ecosystems. What you will also notice is that in the Arctic, it's even darker red, showing that the warming in the Arctic is considerably higher than in the rest of the globe. In fact, in this high warming scenario, RTP 8.5, the Arctic warms by up to 10 degrees, and this is huge, and this will have a huge impact on permafrost. And not only that, but there is this feedback from the permafrost system into the climate, which is not yet included in these models. And this is known as the permafrost carbon feedback. This starts with warming. So the warming begins to thaw the permafrost, and as we've seen, this permafrost thaw is already happening. And as we've also heard from Julia, there is a lot of carbon stored in this frozen ground. And when the ground is frozen, it can't decompose. But as the permafrost starts to thaw, this carbon is starting to decompose. And this results in the emission of additional greenhouse gases from the soil to the atmosphere, in particular carbon dioxide and methane, which are both very important greenhouse gases. And this in turn leads to increased greenhouse effect and increased climate warming, which thaws the permafrost more, and so on. And we have this feedback loop, which somehow amplifies this effect. So you get more permafrost thaw, and then more carbon being released, and more warming, and so on. And this is known as the permafrost carbon feedback. And I mentioned it's not included in these models in the IPCC. And why is that? That's because it's very, very difficult to include this process in these models, because there are a lot of challenges and a lot of uncertainties. And I'll just talk a little bit about this. So firstly, we know that there is a lot of carbon stored in permafrost. In fact, it's over half of the total soil carbon on the whole Earth is found in permafrost soils. And as we saw before, it's significantly more carbon than is actually currently in the atmosphere. So this can be really important. We know there's a lot of it, but it's also very heterogeneous. So you can see these areas, some areas in black, where there's really a lot of carbon, and then some in the blue and gray where there's hardly any at all. And this varies on very, very small spatial scales, so like from a few meters to the next. We could vary from having almost no carbon to having loads, and so it's very difficult both to measure and to model this. Second issue is if you want to include a permafrost carbon in the climate models, of course, you need to include the permafrost itself, and you need to predict how much of it will thaw. These plots show the permafrost in the IPCC models. If we focus first on the gray areas, these areas are where there is permafrost. Historically, there has been permafrost there. But in these areas, all of the models agree that this permafrost will be lost in the future. On the left, we have, again, this low emissions scenario with the lower warming. And you can see the gray areas are significant. They're very large areas, but not nearly so big as in this high warming, high emissions scenario on the right-hand side, where a very large proportion of the permafrost will thaw and will be lost in the future. From these plots, we can also see some of the uncertainty. So the colors, if we look at the colors, the green is showing where all of the models pretty much agree that permafrost will still remain. But in the purple kind of areas, like here, the models disagree. Some of the models predict that permafrost will remain, some of them don't. So this is due to all these complex processes that we've heard about before. And it's an additional uncertainty when we're making these estimates. So now I'll just show you the estimates that we have so far. This plot shows the total amount of carbon that will be released from permafrost. In the dark red, it shows the total amount that we estimate to be released by the end of this century. And so along the bottom axis, that's the total amount of carbon that's released. And then each bar shows a different estimate from a different publication. And the reason that they're different is because they're using different assumptions, different techniques to fill in the gaps in the data and the gaps in the knowledge, which we've already heard about. So we do have a big range from the lowest estimate, 37 gigatons, to the highest estimate of 174. But nonetheless, these are all substantial amounts of carbon. And for reference, this total carbon release would lead to maybe 0.1 to 0.3 degrees of warming. And this doesn't sound very large, but in comparison with the total amount of warming that we want to constrain ourselves to, this is a significant fraction. And another figure that's interesting is, so we have about 100 gigatons of carbon that we expect to be emitted by the end of the century. We actually, if we are to stay below 2 degrees of warming, we have maybe about 600 that we can still emit ourselves. And this 100, 600 is a significant fraction, and it does influence policy decisions. And we need to include it in the models. something I should also mention here is that most of these estimates don't include this closed loop where the extra carbon coming out feeds back to the warming climate. And this brings me on to page 21. On page 21, we've been working on actually representing this full permafrost carbon feedback in 3 of the IPCC models, and this is the first time that 3 of these models have come together to work on this. We work on both the physics of the permafrost in the models and also the carbon processes of carbon storage and decomposition. And we're now making new simulations, including this full closed feedback loop and the impact of the permafrost carbon on the global air temperatures. There's a lot of interesting science coming out of this. Page 21 is finishing now, so this brings me on to the next steps. Currently, it's very widely agreed that an IPCC special report on permafrost would be a very important thing to produce, and I believe some work is already going on in this direction. Secondly, as I've discussed in my talk, including permafrost carbon in the next generation of IPCC models is essential. And from the fieldwork side, we have here operationalized monitoring networks. And what we mean by this is for the permafrost to be monitored in a continuous and systematic way. Because at the moment, it relies on researchers who are maybe on projects of a few years, and then they may change to a different site, and they can't be there all the time monitoring it. Whereas other essential climate variables like air temperature and precipitation are measured by weather services, and they have this continuous records. And so this is something that we would want for permafrost as well. And hopefully you can see from everything we've said that it's very important to do this. Finally, we need to develop adaptation and mitigation strategies to take permafrost regions and the people living there, and also the whole global community forwards into the future. And it's our decisions that determine that future. So finally, we are very grateful for this opportunity to speak today. And we pass many thanks on to the Page 21 team. And thank you all for your attention.